And now for the solutions to the D1 reflection problems.
So a lot of you like, this family question. This is pretty rough. Now, if you watch the notes, so page 5 of your notes, if you have not watched the notes, I want you to copy this down, all right? So we're looking at a family, and, where are they? I'm in the wrong screen. There we go. So we've got 2 parents. And when you all, I know there's a continuum of things as you guys get older, but pretty much when you're born, they tend to say boy or girl, right? They don't really say, all that other stuff. So we're keeping it simple. Now, normally, what's the probability a baby is a boy? Yeah, and probability the baby is a girl? Yeah, unless you're in China. Oh, why? Why?
Because of one-child.
Because of one-child policy. What happened to China?
They all wanted boys.
Why did they all want boys? So they could work, take care of the parents, that sort of thing, right? What happened? There are too many boys. They don't have enough women, so now they're trying to get more women. So, yeah, that's what happens when the government gets involved. All right, so, but for our problem, we're doing normal. I think there is a slight, very slight difference in the boy-girl ratio on birth, but it's super slight. So we're going to keep it at the 50-50. So you should have made this tree. So when I was explaining this tree in the notes, you've got the first baby. There's 2 possible outcomes, right? Technically, there's also some other ones, which is really rare. We're not dealing with that. All right, boy or girl, right? Boy or girl. And then this family wants to try and keep trying until they have 2 girls. But if they hit 5 kids, they're like, no, I don't have room in the car for 5 kids, that sort of thing. I don't want to have 5 bedrooms or whatever it is. They're like, we're done. After 5, they don't want 6 bedrooms, all right? So is this family going to try and have another baby, the top one? Yeah, they're going to try. All right. And so this family has 2 boys. So what are they going to do? They try again. So we keep having them try. We got this top family. They ended up with 5 boys. All right. Now this family ended up with 4 boys and 1 girl. Is this family done yet right here? No, because they're going to try again. They only got 4 kids. They want to give it one more shot for the girl. So one of them didn't make it. One of them did. This family's not done yet either. So they're going to try again. This one's going to try again. But that one right there, they've already got 2 girls, right? And then, so that's pretty much it for the top half of the tree. The bottom half is a lot smaller because you already had, this part here. So this family's done, but this family's going to try again and again. And there you go. So it is possible to have anywhere from just 3 kids on the top tree up to 5. In fact, a lot of those families are 5-kid families. Then on the bottom side, they got a girl on the first go. So, but they're still going to try again because they want another girl. So they got 2 girls here, and this one has a girl boy. They're going to try again. So if they get a boy, they're going to keep trying until they either get the girl or they hit 5 kids. So basically what I did is I wrote out the sample space. So one of the families is boy, 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 boy. What's the probability of that happening? I appreciate your patience and actually saying that out. I'd rather say 0.5 to the 5th because I'm not as patient as you. Yeah. So pretty much any of those 5-kid families, they're 0.5 to the 5th, right? Now, some of them have 1 girl, some of them have no girls, some of them have 2 girls. All right, and then the bottom one, we don't have as many branches because they had started off with a girl. So the 5-kid families, pretty much a 0.03125% chance for each of those variants of a 5-kid family. Now, the model, this is straight from the notes. This is how many kids they have. And then we figured out the probabilities of them having that many kids. So there's like a 30% chance that you're going to have, just over 30% that you're going to go all the way to 5 kids. And all those should add up to 1. So I'm going to let you copy that down. So we come to the question, what is the probability that a family has no boys? Well, there's only one way that happens. You have girl, then girl. Now, some of you, did you really need the tree to figure that one out? No, you didn't need the tree. You could have just gone 0.25 by 0.25, right? Okay, next question. What's the probability a family has one boy? There were two ways to do that, right? And you can see, so I just added both those probabilities to fill in the table. So far, so good? All right. Now we have, what's the probability to have two boys? There are three ways to do that. Interestingly, they always have the same probability, which makes sense. If you have three boys, that means you've got your two girls, right? Wait, three boys? Yeah. Oh, two boys. You definitely got two girls if you stopped. If you stopped at two boys, because you have less than 5 kids. Then we have 4 boys. And then finally 5 boys. Right? 3 boys and then 4 boys and 5 boys. So go ahead and put this table in your calculator. If you need to get one of my calculators, get one of my calculators. Do you remember how to put the table in the calculator?
Yeah.
Now, I didn't really have a reflection where I asked for the average number of boys. I don't think I did. But we do talk about the distribution. So later you will need to know what is the average, what is the standard deviation. So you need that for the next question. So we are going to calculate it. Now, there are a couple different ways to calculate it. One way you can't. Do you guys have this table? Pretty much. Anyone? Oh, if you have the table in already, go ahead and make sure your cups are green at your table, so I know that you guys are all done. All right. You have a question?
Yeah.
What's your question?
How we even got to this one? Like, what is probably that family has 2 boys? Like, when I look at all my sample spaces.
Yeah. How many of them have 2 boys?
Wait, 16. Oh, you add them?
Yes. There's more than one way to get 2 boys. In fact, there are 3 ways to get 2 boys. You should see 3 outcomes.
I do.
Yeah. Okay, so I'm going to go ahead and move on to, this is the expected value. This is the by hand calculation. Now, no one in their right mind is going around calculating these by hand. I promise you that. That's annoying, all right? Unless they're taking an AP exam and they kind of want you to show something like that, all right? They might expect you to fill that out. I'll try to have better guidance as we get into the spring when that is appropriate. But you need to be able to show that. It's really more for other things, not so much. You also should be able to show the by hand. By the way, that's sigma down there, not sigma squared for the 1.494. You should also be able to show the by hand for standard deviation. It's a pain in the butt. I never do it. Instead, I go to other things like, come on, Staplet. So I'll show you how to do this on Staplet because sometimes you get better visualization tools. You can see histograms, all that sort of stuff. It's a lot easier. So basically you click on discrete random variable. So you see how it says discrete random variable on top. We're doing this is for the number of boys. And, you know, one reason I was wondering if my kids did better than district last year, I was like, is it because I taught them to use Staplet? And I think in a way it did. I was like, well, did they cheat with the Staplet? No, my paper kids did better too. So it wasn't just using the Staplet. So Staplet's really handy. I like it for visualizing things because calculators, they're a little harder to visualize, right? And finally, almost down to our family of 5 boys, and then we hit begin analysis, and you have a beautiful histogram, and if you scroll down, you can see your mean and your standard deviation, all right? So technology will do it for you. The problem is you guys are thinking, well, that's no good because we can't use Staplet on our quiz. Oh, okay, maybe we'll use a calculator. So you have your data entered, and right now I am actually going to enter the data. That part you already did, right? So you hit stat, you hit edit. How many lists do you have in there?
2.
You have to. I'm having a clear list, so I have to go clear, enter. So you can go up to the list name to clear the data. And then I go in and I put in all the data. So I'm typing in the 0, 1, 2, 3, 4, 5, and then I'm putting in the probabilities. All right. So if you want to run the analysis, you're going to hit stat calc. Go ahead and hit stat calc. And then select one of our stats, but don't hit all the enters yet, or drop your calculator. So hit stat calc, one of our stats, but there's an important thing to notice. You're going to have 2 lists, not just one. All right? So to get that second list, you hit that second button. Let me see if I can pause this for a second. So let me scroll back. How do you do that? I hit that second button right there that's currently red.
Under the frequency list one?
So you're currently in one of our stats, right?
Yes.
Yeah, so for frequency list, we need another list in there. All right? And then you hit that button that's red right now, the second button. And then you go to the stat button, because that's a list button. All right? And then it's going to give you a list. We want list 2, so we can scroll down to it. All right, there's list 2, and I just hit enter. Okay? So now I have both lists in there. Okay? Then everyone have that set up? And then basically you just hit enter and it'll give you your results. Okay, so there are the results. That should match what you got. Is there something weird about the output on this one? Does it look like the calculator missed something? Oh,
That's
completely blank.
isn't that
It's standard. S of X and sigma of X are related, right?
Yeah, one's a population, one's like a sample.
One's a population, one's a sample.
I think
Wait.
sigma's the population,
Sigma is the population.
which means we're missing.
Why aren't they doing a sample for this one?
Because we're talking about you.
Why are we do we know the entire population? Do we know 100% of the population in this one? Are you sure?
Well, yes, we do, because it's probably similar.
Oh, all those probabilities, what do they add up to? We've got the entire population. Ah, very interesting. So this is one of the few instances when you have a distribution for a random variable. If you know all the outcomes and the theoretical probabilities, you actually know the population. All right? So you do know it. Okay. So it only gives you sigma for that one. All right. And so which of the following statements about the distribution of the number of boys is incorrect? Let's see. I wonder if I can pull up my unfortunately, I don't have the data in it. You can actually do a histogram on your calculator. How many of you know how to do that? A couple of you. I do have notes on my website on how to do it. Someone can remind me and I can try and make it real obvious so you learn that particular skill. Or you can, guess what? You can say histogram TI-84 on YouTube, and there are plenty of videos, all right? I think I have one too. All right, so which statement is incorrect? So it's much easier for me to visualize with the Statlet, so I pulled up the Statlet histogram. By the way, I didn't play with the settings. I just let it be the natural histogram. Yes. Now, your histogram actually looks different than mine, doesn't it?
You do excess and frequency just one.
Well, yes, but here's the difference, all right? So when you're hitting, go back to your graph. And then I think it's window. Click window on yours. You see how you can change the bin width and the starting points?
Yes.
That's so the histograms will look different depending on what you use to create it. If you're creating it yourself, then it could be whatever you set. Huh? It does. Oh, yeah. If you play with it, it can really. That's why I hate histograms. I actually hate histograms. I think they're terrible. I mean, they're nice, but they can change shape. So you can really manipulate a histogram. All right. So here's the default histogram we have. So I just used what Staplet generated. And yeah, the number of boys in many, many similar families vary about 1.5 boys. Luckily, I don't need the histogram for that question. That is the definition of a standard deviation, right? Standard deviation tells you how each individual data point typically varies from the mean, right? Then we have, if there are many, many similar families, the average number of boys is 1.8. Now, personally, I feel better if it said about 1.8, but yeah, if you say many, many, that kind of hedges your bets. All right. The distribution of the number of boys is skewed to the right. Well, based on this histogram, and actually your initial one was skewed to the right. All right. The center of the distribution is an average of 1.8 boys per family. So that's the mean. They said average. The median, now personally, I think the median is probably a better description of center for this one. The median is 1.5. And if 10 similar families are attending the movies, there will be 18 boys at the movies. So which one of those statements is incorrect? Why? There are a couple. First of all, is it many, many families? It's 10. Very small number, statistically speaking. And also, I hate that word right there. Will be. Oh my goodness, you're being way too certain for such a small sample. All right? So that doesn't normally happen. Okay, then we had some of you struggle with the probability density curve. Probability density curve, you learned about one, which is super popular. It's on my toy. This is a probability density curve, right? Shows you where most of your data points are. So this is the normal distribution, right? Such a fun tool. But here, is that a normal distribution they're talking about? No, what did they say? It's uniformly distributed. What the heck does that mean? They're all the same. Now let me hang up on this person. All right. So I am cold-hearted when people call me during class, unless it's a doctor. All right. So what that means is pretty much it looks like a rectangle. And the area of any distribution is always 1. So it's a rectangle because it's going to have the same height throughout. That's uniform. This has the same probability throughout the range. Now, what goes on the x-axis? It is minutes, right? So we put minutes on there. Where does my probability start? It starts at 0, which makes sense. We don't normally have negative minutes, right? So I'll have a 0 at the beginning, and it ends at 50. All right. If it's 50 wide, can I figure out how tall it is? Yes, because the area is what again? 1. The area is 1. So this is actually, oh my goodness, my 6th graders could have figured this one out, right? When I actually started teaching at the 6th grade level, which was fun. It was a blast. First week of school, I'd always have a couple of kids say, "You're the best teacher in the whole world." 6th grade, regular 6th grade math. For some reason, I don't get so many seniors coming up to me saying that first week. I don't know why. Probably because you become jaded. You're cynical. All right. So we know the height is going to be 0.02, so I can put that on my axis, and that's what the distribution should look like. The height is 0.02. That's okay. I have a lot of fun working with you guys, too. 6th graders are fun. They're just exhausting. So when I call you my slothful seniors, sometimes I'm very happy you're slothful. You're not as high maintenance as my 6th graders were. I don't have to plan every minute. You know, 6th grade, you have to plan every minute. Otherwise, your room explodes. Can you imagine? You remember when you were in 6th grade. So now they ask, what is the probability you wait less than 10 minutes? Now, some of you go, but okay, does that marker go exactly on 10 or does it go just under 10 for continuous distributions? We don't care. We're fine. We're going to say it's 10. Okay. So the width there is from 0 to 10, right? If the width is from 0 to 10 and we know that the height is 0.02, right? We just take width times height. and you multiply it out, and you get 0.2. How are we feeling on this one? Thumbs up, thumbs down, thumbs sideways. It's weird, yeah, because we don't normally see it. I can give you a triangular distribution too, or even just a slanty. Well, it'd be triangular, right? So it'd be like this. Could you calculate the area for a triangle? Yeah. Or even a trapezoid. You guys remember your trapezoid formula?
1/2 times A plus B times height?
Base 1 plus base 2. The average of base 1 and base 2 times the height. Yes. Yes. All right. So we'll go to the next one. Which of the following are true statements? The area under a normal curve is always equal to 1, no matter what the mean and standard deviation are. The smaller the standard deviation of a normal curve, the higher and narrower the graph. And normal curves with different means are centered around different values. They're all correct. Oh, shoot. Darn, I'll have to download it. All right. So, the correct answer in this one is all of these are correct right there. All right. Next one. Let's take a look. I presume that one's fun. Last but not least, that one. Well, it's almost last but not least. Okay, so on this one, we're saying which of the box plots can the above histogram correspond? So for me, the easiest place to start is the median. Based on the medians, which one of those for sure is not right?
A.
Correct. I agree with you. The median is not at 50. Let me try and figure out what the median is. I'm going to take those 3 boxes on the right and scoot them over. Could the median be somewhere from 20 to 30? No. All right. So if it's not 20 to 30, so that means it's one of these two. All right. So it's not A, B, or C. It's either D or E. Which one is it? It is D is correct. All right. And also, you can see the blue bars by themselves. It can't even be as high as 30 for Q3. All right. At the right is a dot plot for a set of numbers. One element is labeled X. Which of the following is a true statement? So we look at the Z-score. Z-score for X should be pretty darn close to 0 because it's close to the average, right? X has the smallest absolute value of any element in the set. I have no idea. I don't know what the values are for that dot plot. It could be starting at 99 for all I know. All right, so there are no numbers on the scale. Then box plot will plot a point like X as an isolated point. Box plots only isolate what kind of points? Outliers. Is that point an outlier? No, that's no outlier. All right. Let me go ahead and put that. And D, it might be a stem plot would show X isolated from 2 clusters. Probably, because first of all, you're probably going to have at least 4 stems, right? Which means you'd be dividing that up. I don't know where the stems would start and end, but I'm going to guess that X would not be with one of the stems. It probably, okay, but I don't know for sure because I don't know what the stem plot is. All right. This is only one set of data. We can't do it back to back. And I said cluster. Really, I meant stem plot. So that's a typo on my part. Okay.
An athlete suspected of using steroids is given 2 tests that operate independently of each other. Test A has probability 0.9 of being positive if steroids have been used. Test B has probability 0.8 of being positive if steroids have been used. What is the probability that neither test is positive if the athlete has used steroids? So I'm looking at the probability of both tests being negative, and they are independent. There's no reason to think test A influences test B, so I can just multiply the probabilities. But remember, I'm looking at negatives, not positives. So I need to subtract the positive probabilities out, and I get 0.1 times 0.2, and my answer is 0.02. In a sample of 275 students, 20 say they are vegetarians. Of the vegetarians, 9 eat both fish and eggs, 3 eat eggs but not fish, and 7 eat neither. Choose one of the vegetarians at random. What is the probability that the chosen student eats fish or eggs? So I'm going to create a table. I could also do a Venn diagram. Both of them work pretty well. They actually have 4 areas each, so it's fine. So there's my table. I have eat fish, don't eat fish. Eat eggs, don't eat eggs. And they tell us 9 eat both fish and eggs. 3 eat eggs but not fish. So that would go on the right here. And 7 eat neither. That goes on the bottom right. Now, that means I have a total so far of 19 students and 20 are vegetarians. So I'm just have 1 left over and I put them right there. And I'm interested in those that eat eggs or fish. That would be those people right there. Add those up, divide by 20, and you have your probability of 13 over 20. Last but not least, Jorge's score on exam 1 in his stats class was at the 64th percentile of the scores for all students. His score falls where? Well, 64th percentile, I can see lots of means and medians and quartiles. It's between the 50th and the 75th percentile, so it's between the median and the 3rd quartile. And that's it.